guys, today we will cover flexural design of beam section. What we did before, we determined the moment strength capacity of different cross-section profiles. In this case, we don't have anything except the external load, and we have to determine the cross-section, we have to determine the area of steel, the number of steel rebars, which type of compressive strength we want to use, number grade of steel, etc. All of this we have to determine on our own. So we design philosophy here that we need to produce or to design the cross-section which will have better capabilities to resist the external load. So what we have here, this is the design philosophy. We need to figure out if we have which type of system we have, if we have simply supported beam, continuous beam, etc. To determine the extreme value for the moments, positive or negative, and to find the area of steel, yielding stress, depth of the beam, the depth of the witness block, etc. So again, we are working with extremes here. So what we have to determine, moment using the external load. So we need to figure out if we have only dead load, live load, earthquake, wind, etc. And to determine if we have a simply supported beam, to use Q²/8 for distributed load, if we have a point force, if we have, I don't know, continuous beam. In majority of cases, we are using software to determine the extremes in continuous beams, or you can use the ACI M and V coefficient method. Again, this is way before than softwares, but for continuous beams, in majority of cases, we are using the software. So we need to find the extreme values for the moment. And then when we have all of these, we are using the equation for moment strength capacity. If we are talking about single beam, that strength reduction factor times the area of steel times the yielding stress times d minus a half. This d minus a half we are calling lever arm distance, or JD, and for JD we are using 0.95 d for slab, and if we have a beam we are using 0.9 d. So again, we can use this in equation and to determine that the area of steel is higher or equal than external moment over phi, which is strength reduction factor, over Fy, which is yielding stress, times JD. If we have only external loads, we need to use reinforcement factors. The case reinforcement ratio, we have that area of steel over B times D. Then for singly reinforced concrete section, we are using beta 1 FC primes over phi times Fy. So for doubly, it will be instead 3 times Fy. Then we have reinforcement index, which is given using the reinforcement ratio. Then we are multiplying with yielding stress over compressive strength of concrete. And we have reinforcement factor R, which is reinforcement index times FC prime times 1 minus 0.59 omega. So for single beam, I already gave you this reinforcement ratio. For doubly, again, it is very close to beta 1 times FC prime over 3 times Fy. Using the equation for equilibrium for the resultant force, where compressive force in concrete has to be equal to tensile force, we can determine the depth of the witness block as area of steel times Fy over 0.85 times FC prime times P. And again, if we multiply and divide by D and manipulate, we can say that depth of the witness block is equal to reinforcement ratio times Fy times D over 0.85 times FC prime. We can use rho times Fy over FC prime as reinforcement index, and our depth of the witness block becomes reinforcement index times d over 0.85. Using the equation for moment strength capacity, we will have that area of steel times Fy, which is our tensile force, times d minus omega d over 0.85. Again, we can manipulate this equation and we will get area of steel times yielding stress times depth of the cross section multiplying with 1 minus 0.59 times omega. If we multiply everything with b times d fc prime and divide by b times d fc prime, we will obtain that our moment strength capacity is equal reinforcement factor times b times d squared. So if we have a rectangle section, we will obtain using this equation that d is higher or equal third root of mu over phi times r times 0.7. So again, we need to know how much is the concrete cover. That is something which is given in code, the guidance when we are doing our design. And for beams, columns, pedestals, and tangent ties, the cover is minimum 1.5 inch. That is given in ACI table 20.6.1.3.1. And you have again some ACI guidance for minimum spacing for the main rebars. You have 25.2.1 for one layer of rebar, 25.2.2 ACI code 2 layer of rebars, and for columns we are using 25.2.3. So how to find the spacing? That will be B minus 2 times side cover over the number of space between rebars. So here you have some ACI parameters for cross-section dimension. You have minimum thickness for slab. This is when we are tracking for deflection control. For simply supported beam, that will be L over 16. L is the total span of for total span length. And you have minimum thickness for the slab is 7.3.1.1 in ACI code, and this is the requirements for the beam, which is given in ACI-9.3.1.1. So I gave you here some beam design example with some external dead load. You have live load, superimposed dead load, but the dead or self weight of the beam is not given to you. What else is given? That we have simply supported beam with span length of 20 feet. Which supports all these types of load. You have compressive strength of concrete, which is given 4,000 psi. Then you have yielding stress, which is 60,000 psi, and modulus of elasticity, which is 29,000 ksi. So we need to figure out the cross section. So what we don't know is self weight. Again, we need to assume some depth of the beam. This is in the textbook, given that height is equal something between L over 18 to L over 20. So using the R values, we will get something between 13.3 inch to 20 inch. So it's your call, it's your design. You can pick 14, you can pick 16, 18, 20, it's up to you. In this case, they picked that height is equal 16 inch. So the second step will be to determine the concrete cover. Again, this one is given in ACI code, and for beams, we are using minimum 1.5. So if we are using 1.5, that means the depth of the cross section is 14.5 inch. So the next step is to assume the value for B. So we can use something between D over third to D over half. So that one is given something between 5 and 8, and let's be on the safe side, use for B to be 18. So this is some approximate value, and this one is the next step is self-weight of the structure. So step number 4, you have the width and height. We need to multiply with weight of concrete. So self-weight will be 0.133 kg per feet. The total dead load in our case is 1.083. Live load is 1.5. We are using safety factors 1.2 and 1.6 to determine the total load on the beam, which in our case is 3.69 kg per feet. So again, we have to find the external moment. Since this one is simply supported beam, it is WL square over 8. So 3.69 times 20 square over 8 is giving us 184.5 kb feet. Reinforcement estimation, so we are using rho. Since that we are talking about single reinforcement concrete section, I gave you equation beta times FC prime over 4 times yielding stress. So in our case, 0.85 times 4 for compressive strength over 4 times 60 KSI. You will get some reinforcement ratio to be 0.01416. Reinforcement index is without values 0.21 and reinforcement factor 0.75. So now we need to do selection of cross-section dimension with this weight, with this reinforcement factor to determine the depth of the cross section. So we are using BD square to be higher or equal mu over phi times r. With our value, we are using D to be higher than 16.73 inch. So let's say that our D is 17 inch. You can use 17.5, then you will get height to be 19 or 18.5 to have height of 20. Again, it's your design, it's your call to determine D. So I use 17 inch cover 1.5, which is giving me height of 18.5. In this case, we said that B is equal alpha times D, so 0.7 times 17 will give me B of 12 inch. So our new cross section is 12 by 18.5. Now we need to recalculate self weight based on actual dimensions. So our dead load will, in our case, will be 1.18 kb feet. You have live load, and the total load will be 3.81. So maximum moment will be 190.8 kb feet. So even this is the check for deflection control. What will be the minimum depth of beam based on deflection? So we said we are using table number 9.31-1, L over 16. With our values, age minimum is 15 inch. We have provided 18.5, so we are okay and we can go further. Reinforcement design. So we found that rho is equal 0.0146. We figure out B and D to be 12 and 17. So using the equation, area of steel is 2.85 inch square. So what we can pick for number 8, which is 3.16, 3, number 9, which is 3, or 2, number 11, which is 3.12. Or in our case, we can pick 3, number 9. Again, it's your design. You can pick 4, number 8, or I don't know, number 10 rebars. I picked 3, number 9, which is 3 inch square. Reinforcement spacing. Again, you have maximum spacing S of the form reinforcement shall be the lesser of 3H and 18 inch. So in our case, the spacing will be 12 minus 2 times 1.5 inch, over the 2S, which is the space between 3 rebars. So spacing will be 4.5 inch. According to the codes, maximum spacing is minimum of 3H, which is 54 inch, or 18 inch. We have 4.5, which is less than 18 inch, so we are okay. The next step, we have to check for design. So everything what we did for singly reinforced concrete section before, we need to find what will be the depth of the witness block, what is the location of neutral axis. So this is chapter number 4. So using our values, it will be 4.41 for the depth of the witness block, and we have the location of neutral axis to be 5.19. The strain in steel is 0.0068, which means that tension controls, and in our case, strength reduction factor is 0.9. So moment strength capacity is 0.9 times area of steel times yielding stress times the lever arm. So this one will give me the value of 199.73 kg per feet, which is higher than external moment, which is 190.8 kg feet. So we have a good cross section. Once, when you're doing design, don't do over design. Nobody likes over design. Why? Because you're wasting money. So in our case, go something 8% to 10%. That means that you have good cross section. Everything above 10 and 15% will give us over design, which means we don't have cost-effective solution. So that this one is the example how to do design of the cross section. I will show you in the next videos. You can use some tables, which are also I'm giving you in ACI handouts. And using these tables, I will explain one more example. So that will be the next video. See you for next time and have a great one.